Good morning, everyone. My name is Dr. Krishna Dinda. In this presentation, I will briefly discuss my completed PhD research titled Development of a Non-Stationary and Non-Gaussian Coppola-based Simulation Model for Recoverable Reserve Estimation with application to a porphyry copper deposit. The evaluation of recovery reserves is an important component of long-range mine planning since it directly influences economic decisions and production strategies. However, reserve estimation is challenging due to several practical issues, including limited exploration data, skewed and heterogeneous ore grade distribution, and gradual transition between ore and waste contacts. These features introduce significant uncertainty that must be modeled realistically. Traditional geostatistical methods rely primarily on variogram-based modeling. Variogram only capture the linear spatial dependence and assume Gaussian and stationary behavior. In addition, Kriging variance reflects sampling density rather than the actual grade uncertainty. As a result, these methods tend to oversmooth grade variability and produce biased reserve estimates, particularly near soft ore and waste boundaries. To overcome this limitation, this research adopts a coppola-based modeling framework. Coppola separates the marginal distribution from the dependent structure, allowing spatial dependence to be modeled independently of the marginal grade behavior. This enables the capture of nonlinear and asymmetric spatial dependence, providing a more informative description of the spatial relationship than the variogram-based approaches. In particular, in non-Gaussian copula, specifically the V-transform copula, is introduced because ore grade data are skewed and contain extreme values and exhibit asymmetric dependence. We know that the Gaussian copula only captured the symmetric dependence and failed to capture the tail behavior, whereas the V-transform copula introduced flexible transformation parameters that effectively model asymmetric tail dependence and heterogeneous spatial structure. In addition, non-stationary modeling also is required because mean cumulative distribution function and spatial dependence change across the ore body. This variation violates stationarity assumptions commonly used in classical models. When stationarity is assumed, boundary delineation becomes poor and reserve estimates become biased. Therefore, a non-stationary and non-Gaussian copula simulation model is essential for recoverable reserve estimation. Therefore, the objective of this research were threefold. First one is to develop an automatic boundary detection algorithm for identifying ore and waste contact under sub-boundary condition. Second one is to theoretically develop a non-stationary V-transform copula-based simulation model for recoverable reserve estimation. Third one is to assess the performance of the proposed non-stationary model by comparing it with its stationary model and to nonlinear geostatistical techniques such as multi-Gaussian kriging and disjointing kriging. The developed methodology was applied to a Malonskan open pit copper deposit and validated using blast hole information. This case study clearly reveals that the ore body exhibits nonlinear and non-symmetric spatial dependence. Because of this nonlinearity, traditional variogram analysis fails to reveal clear spatial correlation patterns. In contrast, Kendall tau successfully captures the underlying nonlinear spatial dependence present in the data. Further analysis shows that the dependent structure is asymmetric with stronger association at higher grade quantiles, indicating the presence of tail dependence. The V-transform copula effectively models this asymmetric and tail dependent behavior. Also, when we increase the lag distance, we saw that the spatial dependence gradually weakens, reflecting the scale dependent nature of geological continuity. When these dependence characteristics are incorporated into the stochastic simulation, the copula simulation model consistently outperform multi-Gaussian gigging and descending gigging for recoverable reserve estimation. Moreover, allowing the dependent structure to change the spatially further improves the performance. We saw that our developed non-stationary model performs better than its stationary model and other two the non-linear geostatistical techniques. Therefore, we conclude that these results demonstrate that stationary Gaussian assumptions are inadequate for realistic reserve estimation. Explicit modeling of non-Gaussian and non-stationary spatial dependence is therefore essential. Koplova simulation provides a more realistic representation of geological uncertainty and offers a strong foundation of uncertainty-aware mind planning, highlighting the importance of flexible dependence modeling in geostatistics. Thank you so much.